Hi, this is the third video of the lecture series Digital Economy and Data Analytics. My name is Eik van Vuren, and today we're going to talk about a couple of different things, namely model choice, cross-validation, and the bias-variance trade-off. Well, let's start with the first one, namely how to choose between models. Well, in that sense, it is good to go back to the previous video because of the fact that in the previous video I have already been looking at different kind of models. We have already been looking at k-nearest neighbors, and we also have been already looking at ordinary squares as prediction methods that we could use in the case, well, in the previous video we have been focusing especially in the situation in which the outcome variable is continuous. Well, an important question then arises then is, even in the case that you already chose, for example, to go for k-nearest neighbors, then the question that arises is, how large should k in this case be? Should k be equal to 1, so only one particular neighbor that we're going to use, which is the closest observation to the observation that we would like to predict? Or are we going to, say, set k a little higher, say equal to 2 or 5 or 10? Or maybe we're going to use a very high level of k, say equal to 50, 100, or maybe even 200 observations that are going to be closest to the, say, point that we would like to predict. Well, that is an important question, of course, and we try to, well, understand or answer that question today. Take into account that the same things actually are going to arise at the moment that we're going to use the other method that we have already been looking at, say at the moment that we're going to use a look at ordinary squares. At the moment that we are going to use ordinary squares, then you do already know from your econometrics classes that then a very important question that arises is how many, say, features should we actually include? Should we only include one particular feature apart from, say, the constant that we always are going to include? Or should we include more features, say 2, 3, 4, 5? Or maybe we should even include a couple of hundred of different features. And then another important question that arises is, which features should we in fact include? Well, these are very important questions, of course. And the question that arises is, which model should we in general choose, even in the case that we have already made a choice with respect to whether we either are going to use k-nearest neighbors or ordinary squares. Well, today I will actually focus on k-nearest neighbors. Ordinary squares will be discussed actually in videos later on. But let's now focus on k-nearest neighbors. Suppose that we already know that we would like to look at estimate or predict our, say, model or our outcome variable with respect to k-nearest neighbors. Then an important question that arises is, which k should we actually choose? Well, what we should realize is that we do already know the answer to that question because of the fact that we have already been looking at that question at the start, in fact, of the previous video, because of the fact that we do already know something about the so-called risk. And we do know that we should always choose that particular learner, that particular prediction function g that we have over here, in such a way that the, say, risk is going to be minimized. So that implies, as well, a practical example in our case, that what we should essentially do is that we should calculate this risk for every level of k with respect to k-nearest neighbors, and then choose that level of k for which this risk that we have over here is going to be the lowest. So essentially, as a practical setup, what we're going to do is that we're going to start with k equal to 1, and we end up with k equal to, well, maybe could go as large as the full sample size. But that's the thing that we could do. However, take into account that that actually gives us a problem over here. And the problem is actually quite practical, namely that we cannot calculate this thing that we have over here. And the reason for that is in this case no longer because of the fact that we don't know the loss function. We have already discussed in the previous video how to get a loss function. Well, we have seen that at the moment that we are going to be in a continuous case, which we are going to discuss today. Then at that moment in time, we are going to look at the quadratic loss function. However, even we have seen already that if we are more in the situation of a discrete outcome variable, that means classification, then we also do know how to which loss function we should actually use in this particular case. So we should realize that the loss function in this case is not really the problem. The problem, however, is with respect to the distribution of x and y. We should realize that in order to calculate this mean that we have over here, we need the distribution, the joint distribution of x and y, because of the fact that we should realize that this in fact is nothing else as an integral, and that's an integral of either the density function of x and y or the probability function of x and y. Well, it doesn't matter that much what we are going to get, but we should take into account that then we always need at least the distribution function of this x and y that we have over here. And that we do not know. And the reason behind that is because of the fact that we are here talking about data science. And in data science, we never assume that we do know the distribution of our data. Take into account that x and y is our data in our case. And one, particular rule in data science is that we're not going to assume that we actually know the underlying distribution of the data, because of the fact that then data science is not necessary anymore. So therefore we should realize that this thing that we have over here cannot be calculated. So therefore the question arises, what could we do in this particular case? Well, in that sense we can use the famous trick in data science, and that is that as soon as we are not able to calculate something, then instead what we're going to do is that we're going to try to estimate it. So therefore, for a particular, say, prediction function or learner that we have over here, we are going to try to find, say, an estimator of this thing that we have here on the right hand side. Well, that's not so difficult in this case. Given the fact that this is a population mean, according to the analogy principle, we can always estimate it consistently by using the so-called sample mean. What does that mean in our case? Well, that means that no mean, no expectation that we have over here, but we're going to have summation. We're going to sum over all the observations. We still, of course, are going to use the loss function over here, but now over the I observations that we have over here. And we do that with respect to all the observations, all the n observations that we have over here, and we divide by the sample size in order to get this estimator that we have here at the right hand side. And because of the fact that this is our sample mean, the analogy principle says that for any choice of g that we have over here, this is going to be a consistent estimator of this thing that we have here at the right hand side. So at least at the moment that n goes to infinity, if n is large, well then this thing here at the right hand side is going to converge to that thing that we have there at the right hand side. Well, that's already a very good thing, of course, and therefore one thing we can do is that we can introduce here a little bit of notation, given the fact that this thing here at the right hand side is denoted by LG as the theoretical risk function. What we could do is that we could realize that this is actually nothing else. This thing over here is nothing else as an estimator of that thing that we have there at the left hand side. So therefore we can simply write that as L hat G that we have over here. Take into account again that this thing here at the right hand side again is a function of this function G that we have over here. Well, we would also like to give it a name. And the name that we usually give to this is the so-called training risk. This thing that we had over here was usually called the risk, or more particularly the so-called theoretical risk. And because of the fact that this thing that we have over here is based on our training data set, remember that we actually do this over the training data set that we have so far, this is usually called the training risk. And now, based on this, what we can do is that we can now try to do something which seems potentially very promising and actually quite brilliant. That is that what we could do is that we could say the problem that we of course have in our case is that we have a practical problem, namely that what we would like to do is that we would like to, if we would like to find the optimal k for k nearest neighbors, is calculate this thing that we have here at the right hand side for all the different levels of k, and then take that level of k for which this thing that we have over here is going to be minimized. However, we cannot do that, but take into account that we can actually do that with respect to the right hand side that we have over here. So instead of calculating all these things that we have over here, we're going to estimate this thing that we have here at the right hand side for all the different levels of k, and then choose the k for which, well, this thing that we have over here, the right hand side, is going to be minimized. Well, even though this looks very brilliant, we should take into account this is actually not a good idea. And even though at this stage I'm not going to exactly say why, we should realize that that's because of the fact that we should realize that a training risk is always going to underestimate. There is some kind of bias, a lower bias, which is going to underestimate the theoretical risk. And in such a way that we are going to see that the training risk usually tries to, well, not actually minimize this thing that we have over here, but simply tries to fit the training data as good as possible. And we will see that that actually is not always a good idea. Okay, I would like to explain this a little bit more based on a very simple example. In that sense, what we're going to do is that we're going to look at the data generating process. That implies that we have here at the left hand side yi, which is still of course going to be our outcome variable, and at the right hand side we have say in this case g star xi plus ui, where I'm going to make the main assumption, and that is that ui and xi, they're going to be uncorrelated to each other, which means that the mean of ui conditional xi equal to x must be equal to 0. In addition to that, I'm also going to assume that g star x is equal to minus a half x squared plus cx plus the sinus of 4x plus 2. In addition to that, I'm also going to assume that xi is going to be uniformly distributed between minus 1 and 2, and ui is going to be normally distributed with a mean equal to 0 and a variance equal to 0.25. That means, of course, that the standard error is going to be equal to 0.5. In addition to that, we can actually, based on this model, immediately conclude that the best predictor is this g star x that we have over here. And that's not because of the fact that it's called g star x. Remember that I usually denote that for the best predictor, this g star x that we have over here. But in this particular case, we can immediately see that g star x is going to be our best predictor. And that's for the simple reason that we do already know that at the moment that we're going to use the quadratic loss function, then at that moment in time, well, the best predictor that we're going to have is, well, the mean of yi conditional xi equal to x. At least at the moment that this yi that we have over here is going to be continuously distributed. Well, that we can calculate in this case based on this model that we have over here. We can easily calculate the mean of yi conditional xi equal to x, and that's for the simple reason that ui and xi, they're uncorrelated with each other. And if I'm going to do that, then I do actually find out that the mean of yi conditional xi equal to x is actually nothing else as this g star x that we have over here. That actually implies that if we would actually know this function that we have over here, then we don't have to do any data science anymore, because of the fact that then every time that we have to make a prediction, then the best prediction that we can ever make is this right hand side of the function that we have over here, given a particular value of xi. Of course, that is not what we would like to do. What we would like to do is that, even though of course we do know that well, this is going to be our best predictor, what we would like to do is to make predictions without, of course, knowing this best predictor that we have over here, and to essentially compare our predictions with our potentially best, or in fact our best predictor. And that's what we're going to do. And in that sense, it might be a good idea to look at the next picture that we have over here, where I have on the x-axis I have the different values of x, and on the y-axis I have either the function gx or the, say, outcomes that we have with respect to y of our data points. Take into account that what I've done over here is that I have taken values of x between minus 1 and 2, and take also into account that that is the full range that we can actually have with respect to the axis. It's actually equal to the support because of the fact that xi is uniformly distributed between minus 1 and 2. Well, then, in addition to that, we do see that I actually already made here this curve for the best predictor. That is this curve that we have over here. That is this orange curve that we have over here in this picture. And well, this actually does have a very well expected shape, because of the fact that we should realize that the function that we are going to look at is actually nothing else as a mixture of two things, namely a so-called polynomial. This term, and that term gives us actually a polynomial that would just look a little bit like this, but we should take into account that in addition to that, we of course are going to get these waves from the sinus, and that's exactly what we're going to see over here. We have these waves over here, making it a bit more difficult to, say, make good predictions. So, and then in addition to that, we also have our data points, and what I have done is that I have randomly generated 100 different data points, and it's actually quite easily to see that at the moment that we're going to look at these data points, that these data points actually, they are not exactly equal to the best predictors. And take also into account that even though they are not exactly equal to the best predictors, they essentially swing around a little bit around this best prediction curve that we have over here. Well, then that makes sense, of course, because of the fact that we should realize that what are the yi's that we have over here at the moment that we're going to generate them? Well, they're equal to the best predictors evaluated in a particular value of xi, plus of course an error term which is independent from this term that we have over here, and which is simply a normal distribution. So it can take positive and negative values, and you should realize that of course means that, for example, for this point that we have over here, we had actually quite a large level of ui and it was positive, whereas for this point that we have over here, it was also large, but it was negative. And take into account that these are two outliers here, but at the same time, most of the other points, even though not directly or completely equal to the best prediction, not exactly lying on, say, the orange curve that we have over here, they're a little closer. But some of them, they're positive, some of them are negative, and some of them, they're really, really small or only with a tiny difference with the best predictor. So that's the idea behind this curve that we have over here. But now an important question that arises is, could we actually make predictions? Well, in that sense, what we're going to do is that we're going to use our k nearest neighbors predictor. And we can actually do that, and the question then, of course, first of all arises, how large are we going to take k? Well, what we're going to do is that we are simply going to assume that in this particular situation, k is going to be equal to 50, which means that we're going to look at the 50 nearest neighbors to the points that we would like to predict, and we're going to take the average out of it. In that particular situation, what we're going to get is this green curve that we have over here. In order to explain this a little bit better, maybe the best thing to do is to start here in -1. -1 is of course the lowest point that we can ever get with respect to the x that we have over here. And we should realize that, of course, that means that all the other points that we have over here, they're larger than all the data points that we have over here. They are, by definition, larger, of course, than this point that we would like to predict over here. And that means, of course, that the closest points that we're going to have, closest points to -1, they're in fact the, say, 50 lowest points that we do actually observe. And what we are going to do then is, of course, take these points and take the average, and that is this value that we have over here on the y-axis. So that's our predictor. However, take into account that at the moment I'm going to go a little bit higher, then it's still the case that the lowest 50 points, they are going to be the closest points to the points that we would like to predict. For example, here in -0.5, it's still the 50 lowest points with respect to x that we are going to use in order to make our prediction. So in that sense, nothing is actually going to change between -1.5 or -1 and -0.5 with respect to my prediction. However, at a particular moment in time, that starts actually at this point that we have over here, it is the case that, say, there are going to be points over here that are going to be closer to this point over here compared to that lowest point that we have over there. So that implies that we're going to take, say, points over here that are going to be in our nearest neighbors, and because of the fact that these points here are higher than the points that we have over there, that implies that we are going to have higher values with respect to our prediction. And that's what we exactly see. We see that it increases all the time here at the moment that we are going to replace more and more points over here with the points that we have over there in our k nearest neighbor prediction. However, at a particular moment in time, we are going to realize that what we are going to take is all the highest points, not the lowest points, but the highest points with respect to our predictions, and that implies, of course, that we're going to end up at this level that we have over here. So therefore, that is our prediction based, of course, on a k nearest neighbors prediction with k equal to 50. An important question that now arises is whether this is going to be a very good prediction. Well, unfortunately, this is not a great prediction. Actually, what we could say is that this is a horrible prediction. And the reason for that is that what we have to do is that we do not have to make a big comparison between, say, the green prediction that we have over here with the blue dots that we have over here, but we have to actually compare it with respect to the best predictor. We do already know that this is our best predictor, and we immediately see that this green curve that we have over here is generally quite far off from our best predictor. We see over here that it's here much too high, here it's actually much too low, but even here in the middle it's not doing a very great job. So therefore we should realize this is not a great predictor at all. And the question of course arises, can we do any better? Well, one thing that I could have done, of course, is going from k equal to 50 to even k higher than 50. However, that would actually not make that much of an improvement. And the reason behind that is because of the fact that k is equal to 50 is already quite large if the number of observations that we have in total is only equal to 100. So therefore it's actually better in this case to go down with respect to k. Of course I could go down for k is equal to 49, 48, 47, but that would not make that much of a difference, of course. It's better to immediately go down quite a lot, and therefore I'm immediately going down to k equal to 25. Then what we're going to get is this predictor that we've over here. Well, it's immediately clear that this is a much better predictor than what we had originally. So originally we had this prediction over here, which was quite far from the, say, best predictor that we could ever get. And now we get this one that we've over here. And at least in some areas, it does already quite well. It does quite well over here, I would say. Up till here at least. Here it gets a little bit further away from the best prediction. Also here, and especially over here at the top, we do see still quite a big difference between the best predictor and the prediction that we actually make, but it's much better than we have already seen before. So therefore, this is a much better predictor, k equal to 25, than k equal to 50. Question arises then again, can we do even better? Well, we have seen that we have made an improvement by going down from k equal to 50 to k equal to 25, so therefore it might be a good idea to actually go down from k 25 to, for example, k equal to 10. So that's the next thing that we're going to do. Now we're going to look at the situation in which k is equal to 10. Now it becomes immediately clear that we now even do much better than in the case of k equal to 25, because of the fact that this was k equal to 25, where still we had a lot of differences over here, but at the moment that k becomes equal to 10, then the differences are not that large anymore. So we get closer and closer actually to our best predictor. So therefore the question arises, could we even do better by going down to, for example, k equal to only 5? If we set k equal to 5, well then things become a little bit more difficult, because of the fact that now it's not that clear anymore whether this figure that we have over here is better than the figure that we had before. Maybe it is. Maybe this figure actually is still improved by going from k equal to 10 to k equal to 5. For example, here there is still quite some difference for k equal to 10, and that is actually gone away at the moment that we set k equal to 5. But one thing immediately becomes clear here as well is that even though also the comparisons become more difficult because of the fact that both of these curves already are quite close to, say, the best predictor, one thing that we see now as well is that, well, the relationship or the shape of this predictor that we have over here is going to become a little bit more erratic. We do see, for example, over here that it goes up here and then it goes down again, at least if you zoom in, and here it goes down again. We should realize that it becomes a little bit more erratic than what we had before because of the fact that this one, at least, even though we have, of course, these jumps all the time, it looks like it goes more in one particular direction. Here it goes all the time up, and here it goes all the time down. Here again it goes all the time up, and like that. And that's not what we see over here because of the fact that here we do see that it sometimes goes up and then immediately goes down again, etc. So it looks a little bit more erratic. And that's especially what we're also going to see at the moment that we go from k equal to 5 to k equal to 2. Here we immediately see that this erratic behavior that we already saw a little bit with respect to k equal to 5 now is much more important at the moment that k is equal to 2. And one thing that we can conclude from this is that k equal to 2 is actually not such a great predictor. And the reason behind that is even though it generally, of course, follows the best prediction curve, this orange curve that we have over here, at least that sometimes, well, there can be quite a big difference between the prediction that we're going to make and the orange curve. For example, that happens over here as well as here, and we have that in some other places here as well. So at least maybe it's not doing so badly yet as k equal to 50, but we should take into account that going from k equal to 5 to k equal to 2, well, there we actually do not see that we have an improvement. Actually, it becomes worse in this case, and we do see that this erratic behavior also becomes worse compared to k equal to 5. And then finally what we can do is that we can finally also ask ourselves the question, but what is going to happen if k becomes equal to 1? Well, then we get a very special case because of the fact that then we do see that all the predictions actually are going to go through the points that we have over here, the observed points that we have over here, but we also see that, well, the curve becomes extremely erratic, and in addition to that, generally, it's actually quite far off from the best prediction, even though, again, it actually follows more or less this best prediction. In most cases, it's actually quite far off. For example, in this point that we've over here, but also in that point that we've over there are only very few points in which we actually are very close to the best predictor. So based on this, we can make the following conclusion. Well, we can say that k equal to 50 is definitely not a good prediction. K equal to 25 is also not a great prediction. Then scrolling a bit more, well, probably k equal to 2 and k equal to 1 are also not very good predictors. And the best prediction that we can actually think about is, well, either k equal to 10 or k equal to 5, or something in between k equal to 5 and k equal to 10. However, at the moment that we're going to look at the training risk, then we see something completely different. By looking at the training risk, we see that for k equal to 1, based on this table that we have over here, the training risk is actually equal to 0. In addition to that, at the moment that we are going to have k equal to 2, then the training risk becomes positive. It is then equal to 0.1694. For k equal to 5, it's equal to 0.2685, even larger. And we do see that for values equal to, for k equal to 10, 25, and 50, we do even see larger values. We actually do see that the larger k is, the larger also is the training risk. And based on this, we would actually say that well, the best model that we can ever choose is actually k equal to 1, because of the fact that then the training risk is equal to the lowest potential outcome with respect to the potential training risk, because of the fact that then it's equal to 0. And that is, of course, very surprising. But the question arises, does it also make sense? Well, let me first of all look at whether it makes sense or not. And well, that is by looking at what is actually the training risk. What we should take into account is that the training risk in our case is actually nothing else as the difference between, say what we observe, yi, and our prediction, and then taking the squares. And taking into account that we take squares, it means of course that the lowest outcome that we can ever have is 0, and that's only the case in the situation that yi and gxi, they are always equal to each other, which means that our predictions should be always equal to, in fact, the outcomes that we have. And take into account that that is exactly the case at the moment that we are going to go to the case equal to k equal to 1, because of the fact that in that particular situation we indeed see that, well, our predictions, the green curve that we have over here, is always going through all the data points. So at the moment that we're going to look at a data point, then actually our prediction is exactly equal to that particular data point. And that does make sense, because of the fact, what does actually k equal to 1 mean at the moment that we are going to go for a prediction with k nearest neighbors? Well, that essentially means that at the moment that I, for example, would like to predict this point that we have over here, well, then what we do is that we essentially take the average of that point itself, because of the fact that that's this data point, and it actually takes the average of that single data point that we have over here, because of the fact that we are only going to look at the closest point that we have, to take the average over that, and that is of course the value by itself. Well, that is of course very special with respect to k nearest neighbors in the case that k is equal to 1. So indeed we should realize that it makes sense that the training risk is equal to 0 at the moment that k is equal to 1. But the question of course arises, is that also a very good prediction? But the answer to that is obviously no, because of the fact that we do already know that the best prediction is actually this orange curve that we have over here. And we do see that the green curve that we have over here generally is quite different from the orange curve, and that and we also see that at the moment that we are going to go for k equal to 5 or k equal to 10, then we are much closer to the orange curve in general than in the case that k is equal to 1. So the question of course arises, why does actually the training risk at least indicate here that k equal to 1 is much better than k equal to 5 and 10, even though we do see that based on this picture it's quite easy to see that k equal to 5 or 10 is much better than k equal to 1. Well, that has all to do with the fact that we should realize that we have done something, well, what we have done, you could say, is something related to cheating. What we did with respect to our predictions was that we actually already looked at, say, by looking at a training risk, we do cheating in that sense that we, in fact, by making our predictions, we could actually already see what we wanted to predict, namely these dots that we have over here. And then, of course, at that moment in time, it is easy to predict, because of the fact that if I do already know what I have to predict, then at that moment in time, the only thing that I have to do to get the best prediction is just predict the point itself. And that's exactly what we see at the moment that we are going to look at the training risk for k equal to 1. But we should take into account that that's not really the nice way of predicting, because of the fact that this is actually cheating. If you would like to predict something, then it should not be the case that we already know what we actually have to predict. We should realize that, of course, predicting usually is not something from the past, that we would like to predict from the past, but we would like to predict something in the future. We should take into account that it's also the case at the moment that, for example, I would like to predict, say, weather. Of course, for me, it will be very, very simple to predict, say, the average temperature or, say, the max temperature, say, of all the days in the year 2024. That would be very, very easy for me. The reason behind that is because of the fact that, it is not that difficult to see in the internet what actually the maximum temperatures here, for example, in Groningen were in, say, the year 2024. And therefore, it would be quite easy for me to, in fact, make a model that predicts, in fact, for all the different days the max temperature, and I will be able to do that, I would say, perfectly. However, nobody would actually be very well surprised that I would be able to do that. However, in that sense, it's going to be much better if I would be able to make good predictions, maybe not perfect predictions, with respect to the maximum day temperature, not in 2024, but for example, in 2026. People would be much more amazed about my predictive possibilities, my predictive talents, at the moment that I would be able to at least predict more or less the maximum day temperatures of all the days in 2026. And the reason behind that is because of the fact that by, making my predictions for 2026, I can actually not look at yet at the day temperatures in 2026 because of the fact that that didn't happen yet. And you should realize that that's a thing that is usually the case. At the moment that we would like to make predictions, then we would like to make predictions of things that actually going to happen not in the past, but in the future. And we should take into account that by looking at, say, the training risk that we have over here, is that we actually try to predict things that we already know that actually did happen, you could say, in the past. We do already know our data set over here, and that makes it very simple to, in fact, make predictions. In that sense, it would be much better to think more in terms of what would actually happen if I'm not going to try to predict this blue dot data set that we have over here, these blue dots that we have essentially over here, but the question arises, what would I actually get at the moment that, or how well would I actually predict if I use a particular prediction function and I'm going to try to, say, predict data points that I'm going to generate from another data set, not this data set that we have over here that I use, in fact, for the training of the data, in a sense, to make my predictions, but I would, in fact, in the end, like to predict, say, data points that are from another data set, that are not from this data set that I used in order to make my predictions. That is essentially what you usually would like to do. Of course, you would like to use data to make predictions, but then you do not want to predict the data itself, but you would like to use that for, say, future things. Take into account as well that that's the whole idea, of course, as well, with respect to, say, for example, predicting house prices. It's not that interesting to predict house prices of houses that are already sold. Of course, I'm going to use that data in order to, make my predictions, to, in fact, what we usually call train the data, in order to, do the estimation process. But in order to see how well I'm actually predicting, what I need to do is to look at future data. Houses that are, say, sold in the future. Well, that we should realize here as well. And, at the moment that we, for example, are going to go back to this, this picture where k is equal to 1, then you should realize that, for example, at the moment that we are going to get a new data set, and we get an x value that is almost identical to, for example, the value that we have over here, then of course the question arises, does it then make sense to expect that the new value of an x value that's almost identical to this one that we have over here, another time is going to be an outlier and is going to be so high as the one that we predict over here? Well, the answer to that is obvious. Most likely not, because of the fact that this was an outlier. It's much more likely that the new point is going to be much closer to the best predictor, maybe somewhere over here. Or maybe even it's going to be negative somewhere over here. It might even be another outlier, but the outlier could even be somewhere over here instead. So we should realize that this prediction that we have over here, even though it looks really great in this particular setup, because of the fact that we predict very well this point that we have, this outlier that we have over here, in reality, of course, it's not such a great predictor, simply because of the fact that future data that we're going to generate is simply going to give us other outcomes, and probably not this outcome that we've over here. So therefore, this is a long way to essentially say that in order to see how well we are predicting, it's better not to use the data that we have been using to do the prediction, but to use new data. Well, that we can of course quite easily do in our simulation. What we can simply do is to, well, run a new simulation and ask ourselves the question, how well are we actually doing with respect to that new simulation in terms of our predictions? And that's exactly what we're going to do. What we could simply do is do another simulation, and usually I'm going to call that a so-called test sample. That is another simulation that we're going to do in order to find out how well we are actually doing with respect to our predictions. And because of the fact that this is from the test sample, we usually call the risk not the training risk anymore, but we're going to call it the test risk. To give you an idea of how this actually works, well, the thing that we're going to do is that we still are going to, well, do the same predictions as we did before. So based on these blue dots that we have over here, we're still going to make these predictions that we have over here for the different levels of K. But then instead of, say, using this training risk over here to calculate this thing over here over the training data itself, we are going to generate new data in order to calculate this risk that we've over here. And because of the fact that that's on the test sample, we're going to call that the test risk. Well, in our case, what we can do is that we can, of course, another time use 100 observations, but then, of course, it may be possible that that is going to be very dependent on the particular sample that we have. So therefore, what I did here is that I used a very large sample size of 10,000 observations, just to be sure that we're not just lucky with respect to some particular outcomes that we have in our sample. If I do that, then I see a completely different story. Then what we see here is on the x-axis we have the different values of K. So here starting with K equal to 1 up till K equal to 50. And here on the y-axis we either have the training risk or the test risk. And first of all, we do already know that the training risk at the moment that K is equal to 1, then the training risk is always equal to 0. And it increases at the moment that we're going to increase K. So we do see that it actually increases here, especially quite quickly up till K equal to 10. Well, then it stays stable for a while, but it's actually still increasing. And then it increases again. Well, and it's actually quite large at the moment that K is equal to 50. But however, we are going to see something completely different at the moment that we're going to use our test risk. Then we do see that for K equal to 1, well, then the test risk is not very high, but it's not very low either. And it's going to decrease at the moment that we're going to increase K. It's going to decrease, of course, at the moment that we increase K. And, we do see that then at the particular moment in time, it also stays stable for a while. Don't actually know what happens over here. That for that we have to look a little closer in this area that we have over here. But then it increases again. Well, what we can see here, if we focus on this a little bit better, which is difficult to see from this particular picture, that the lowest value is actually at the moment that K is equal to 7. Then at that moment in time, the estimated test risk that we have over here is lowest, and it has a value then equal to 0.2813. So based on that, we can actually say that, in this particular situation, if we do it in this way, then in fact K equal to 1 definitely is not our best choice, and K equal to 7 in this case would be our best choice. And therefore one might say like, well, then just choose K equal to 7 to be our best choice and do any kind of future predictions with respect to K equal to 7 based on the particular example that we've over here. We should realize that if we do that, then we are not testing, in fact, our model anymore. We are not doing the test phase anymore of our model, but that actually what we do is that we do something which is called in machine learning validation. That is usually the tuning of what we usually call the hyperparameters. Take into account that this K equal to 7, or the K in K nearest neighbors, is a hyperparameter that we need to estimate in order to find out what actually our best model is. Well, then at that moment in time, we do something which we call validation, and that implies that then if we are going to use the test sample to do the validation, then we actually don't call it test sample anymore, but then we actually call it validation sample. That implies that in fact in machine learning we always have 3 different samples, That is to say that we have first of all the training sample, that is in order to estimate the model parameters. We have the validation sample, which is used to choose the best fitting model, so to tune this k that we have over here, at least in k nearest neighbors. And then finally we have the test sample to evaluate the quality of the predictions. So the test sample is actually only to find out how well we actually are doing, and that could be compared, for example, at the moment that we're going to compare different kind of methods with each other, because of the fact that k nearest neighbors is of course not the only method that we can actually use. We could, in this particular situation, also have used ordinary least squares or other kind of regression methods that we're going to, well, discuss in the next videos. So therefore we should realize that therefore we would like to make comparisons, and for that we are going to use the test sample. I would like to go on with the last topic of this video, and that's the topic of risk decomposition. In order to start with that, I would like to say that it's tempting to think that the most flexible models make the best predictions. In that sense, it's good to go back to the k nearest neighbors estimator, and there we actually have seen that k equal to 1 is of course a very flexible model, because of the fact that that allows for a different prediction for almost any different value with respect to x, and that is quite different than in the case that we, for example, have k equal to 50, where we have seen that in many situations we can actually change the value of x by quite a bit and not changing the prediction that we're going to make. So therefore what we can say is that the lower k is going to be, the more flexible we are. And it's very tempting to think that the more flexible we are, also the better are going to be our predictions. But this is actually not true, and we have already seen that at the moment that we have been looking at the k nearest neighbors estimator, because of the fact that we have already seen that k equal to 1, the most flexible model, is not also the best predictor. So therefore we should realize that it's actually not true that the most flexible models make the best predictions. And that's because of the fact that flexible models have usually a very small bias but a high variance. And that is something that we already know from econometrics, because of the fact that also in standard linear regression models we do already know that at the moment that we're going to include more and more regressors, then we are going to reduce in fact the risk of having what we usually call an omitted variable bias. So that implies that the more regressors are going to be included, the smaller is going to be the bias. However, generally we also know that the more regressors we're going to include, the higher is going to be the variance. So there we do already see that there is some kind of trade-off between bias on the one hand and variance on the other hand. Well, the importance of this can be seen by looking at the quadratic loss function, and that's what I'm going to do for the rest or the remaining part of this video. For that I'm going to assume the following setup. We're going to have yi at the left hand side, and on the right hand side we are going to have g star xi plus ui, where g star xi now is going to be a variable, very general function of this xi that we have over here. In addition to that, I'm going to make a couple of additional assumptions. I'm going to assume that xi and ui, they're going to be iid, and the conditional variance of ui is going to be equal to sigma squared ux. So the only assumption I actually make over here is that this thing that we have over here exists, but I do allow for heteroscedasticity because of the fact that this thing actually does depend on this x that we have over here. Then finally I'm going to assume that ui and xi, well, they are going to be uncorrelated to each other, which means in fact that the mean of ui conditional xi equal to x must be equal to 0. Well, based on this model that we have over here, we can look at something that we are going to call the mean squared error condition on x equal to this little x that we have over here. What is that? Well, that's actually nothing else as the mean of y minus g hat x squared condition on x equal to x. Take into account that this thing that we have over here already looks quite like the, say, theoretical risk that we have introduced before, because of the fact that given the fact that we have this quadratic loss function in this case, it means that the theoretical risk is simply equal to the mean over x and y of y minus g hat x squared. And take into account that this thing looks a lot like that thing that we have over there, with the main difference that here we condition on the value of x and here we don't. So that's a big difference between the theoretical risk and this mean squared error condition on x equal to x. But let's first of all look at this thing that we have over here and then ask ourselves the question how this thing over here at the left hand side could be related to that thing that we have over there, our theoretical risk. Well, then the first thing that I'm going to do in order to rewrite this is that I'm going to subtract and add g star x here within the parentheses. So what I do here is that I actually first of all have here minus g star x, and then we have here plus g star x. This is of course a very trivial step, but then the next step that I can take is that I can then do something of course with this squared term that we have over here. What I can do is that I can square these two terms, I can square these two terms, and then of course what I'm going to get is a final term which is this thing multiplied by that thing, and then of course multiplied by 2. If I'm going to do that, then I'm going to get to this step that we have over here, and well, take into account that I have done one additional step because of the fact that well, this was of course all under the mean, so that implies that officially what I'm going to get is a mean of a sum, but I can write that of course as a sum of means, these three means that we have over here. So here the first part is related to, well, the first two elements that we had but squared, and this is based on the last two elements that we had but squared, and this is of course the cross term that we had. Well, let me now first focus on this cross term that we have over here, and the first thing that I can do is that I can take into account that this is actually a mean over y. It's not a mean over x because of the fact that we condition here on the values of x. So that means that well, it is the conditional mean of y conditional on x. This means that it's in fact an integral over y, not over x, and that implies that anything that we have here inside that doesn't depend on y but only on x, well, that can actually be taken out of this mean, and that of course implies that this part over here can be taken out of the mean. However, we have to be a little bit careful over here because of the fact that well, g star x, that of course can be directly taken out because of the fact that g star x is non-stochastic, but that's not true for this g hat that we have over here. G hat is stochastic because of the fact that it depends on the data. Estimators are always stochastic. This is an estimator. So therefore, if I just take it out here, out of this mean, then this whole term that we have over here is going to become stochastic, whereas this term over here is not stochastic. So that cannot be true. So therefore, what I have to do is that I still have to take the mean condition, of course, on this thing over here. So that is what we're going to get, is that we're going to get the mean of g hat x that we have over here. So this is now the next step that we are going to take. Then the next step is relatively simple, and that is that this is of course a mean over difference. That's a difference of mean, so I can write this now as the mean of y conditional x equal to x, minus of course the mean of g star x conditional x equal to x, but take into account again that g star x is non-stochastic, so therefore I can simply write g star x itself. So therefore what we're going to get then here in these parentheses is the mean of y conditional x equal to x minus g star x. But now take into account that given the assumption that we've made over here and the model that we've made over here, it's not that difficult to find out that the mean of y conditional x equal to x is just equal to g star x itself, which means that this difference that we have over here is simply equal to 0, which means that this whole term that we have over here is going to be equal to 0. And that implies that I can simply ignore it, and that implies that next to that I'm going to now focus on this term that we have over here. Take into account, by the way, that y minus g star x can also be written as u, because of the fact that if in this model I take g star xi to the left hand side over here, I get ui is equal to yi minus g star xi. So that implies, of course, that I can also write y minus g star x as being equal to u. So therefore I can write this now as the mean of u squared conditional x equal to x. So that essentially implies that what we have over here is the second moment of u conditional x equal to x. Well, in this particular situation we can also write that as the variance of u conditional on x, so this sigma squared ux that we have over here. And the reason why I can actually do that in this particular case is simply because of the fact that we should realize that the variance is always equal to the second moment minus the first moment squared. Well, this is of course the second moment. Then of course we still have to take into account the first moment squared, but take into account that the first moment in this case is equal to 0. That's this assumption that we've over here. So therefore in this particular case we do know that the second moment is equal to its variance. So therefore I can also write this simply as sigma squared ux. So that's what I'm going to do next. Well, then what I'm going to do finally is that I'm going to focus on this term that we've over here. Well, this term I can first of all rewrite by essentially trying to solve with respect to this squared term that we've over here. We can get rid of the squared term, of course, by simply taking the square of this one, the square of this one, minus of course 2 times this one multiplied by this one that we have over here. Then we get this, all these terms that we now have over here. Well, then the next thing that I can do is that I can then realize that this is of course a mean of a sum. That's of course sum of means, but also here we have to be a little bit careful because of the fact that some of the things, they are deterministic, such as this thing that we've over here, g star x squared. Also this thing that we've over here is deterministic, but this thing, for example, is not deterministic. So we still have to keep there the means, and we also actually have to do that over here. So therefore, in order to do it correctly, what I should actually do now is to simply write it in this format that we have over here. We get then the, first of all, the g star x squared. We get here minus 2 times g star x multiplied, of course, by this thing over here. And then finally we get this final term that we've over here. Now focusing on these two terms that we've over here, we should realize that these two terms together, they also already look more or less like a squared term, because of the fact that here we have a squared term, here this term already looks a lot like a, say, cross term, because of the fact that we have here the g star x that also showed up over here. We have a 2 in front, and we of course have this term over here. So therefore, in order to get the full squared term, the only thing that we are missing is this thing but squared. Well, what we can of course do is to add that to this equation, but at the moment that I'm going to add it, of course I also have to subtract it. So therefore the next thing that I'm going to do is that I'm simply going to add this to the, say, whole equation, this term that we've over here but squared, but then I also have to subtract it, and that's what I do over here. And then what I can realize is that then I can write these three terms together as simply being g star x minus this thing but squared. So then we get this thing that we have over here. Take into account, by the way, that if we now look within the parentheses over here, that this actually has a nice interpretation. This is actually the mean of our estimator minus the thing that we want to estimate, because ultimately what we would like to estimate is of course this g star x function that we have over here, our best predictor. So what we can say is that this thing that we have over here, well, can generally be called the bias. This is the bias because of the fact that the bias is always equal to the mean of our estimator minus the thing that we want to estimate. So this thing that we have over here is in fact the bias. Of course it's the bias squared because of the fact that we square it over here. Well, another thing that we have to take into account over here, by the way, is that this is not really the mean of, well, the bias that we have of this estimator that we have over here, because of the fact that this is actually a complete function for any level of x. So therefore we're going to give it a very special name. We're going to call it here the pointwise squared bias. So this is the pointwise bias that we have over here based on a particular value of x, not on the full function g that we have over here. We call it the pointwise squared bias. Well, then we can also look at these two terms that we have over here. This is actually the second moment of our estimator minus the first moment squared. Also, that has a very special name. Generally, the second moment of our estimator minus the first moment squared is of course equal to the variance. So therefore, this can actually be seen as the variance of our estimator. Also, here we have to be a little bit careful because we don't directly estimate here this for the whole function g that we have over here for any x. We only do it for a particular point x, so therefore we're going to call it the pointwise variance. Which implies that now we are going to see that we have now 3 different terms. I'm going to rewrite this a little bit, introduce a little bit of a notation. I'm going to write this pointwise squared bias, in fact, as the bias squared. And that is, of course, dependent on our function g, as well as the point in which we are going to evaluate this x that we have over here. And we can do exactly the same thing with respect to that variance that we have over here, that pointwise variance that we have over here, that we can write simply as var, and then evaluate it, of course, in g hat and x. So then we get these 3 terms. We can simply write it now in this format that we have over here, which says that the mean squared error conditional on x equal to x is based on 3 terms, sigma squared ux, plus the bias squared, plus this variance. Well, this is already quite nice, but we would like now to relate that to our risk function. Take into account that this is, of course, our risk function, as already said, and the main difference between the risk function that we have over here and this mean squared error conditional on x equal to x, as already said, is that this thing is actually conditional on the values of x, and this one is actually not conditional. It's actually the joint mean of with respect to x and y. But we do already know how to, of course, relate a, say, joint mean to the conditional means, because for that we have the law of iterated expectations. That implies that what we can do is that we can simply write this as an integral over, well, we can write this as the integral over, we're going to condition, of course, on the values of x, not on the values of y, so we get the mean of y conditional on x, and then, of course, multiplied by either the probability or the density function of this x that we have over here. Take into account that there is now still a difference between this mean that we have over here, this conditional mean, and that mean that we have over there, because here we have a small x and there we have a large x. But that can be solved quite easily because of the fact that we should realize that this x that we have over here is, of course, equal to that x that we have over there. That one is already equal to little x because we condition on it. That implies, of course, that this one that we have over here is also equal to little x. So therefore we can write it in this format that we have over here. And that, of course, implies that what we have here now in the integral is exactly identical to what we have here at the left-hand side. So what we can do is that we can now substitute these terms into this integral that we have over here to get a very large integral. But take into account that this is, of course, nothing else than an integral of a sum. That's a sum of integrals, of course. So what we can do then, the next step, is that we can simply write it now as 3 different integrals. This integral for the first, say, part that we had over there, this integral for the second part, and then finally, well, this integral for the last part that we had over there. But now we should realize that actually all these terms that we have over here can also now be seen, in fact, as means, because of the fact that what are they? Well, they're in fact integrals over, in fact, the full support of x with respect to its density. So therefore we can write this simply as the mean of sigma squared ux. That means, of course, that this can be written as the mean of the bias squared, and this, of course, as the mean of the variance. So therefore, finally, what we're going to get is that our risk can be decomposed in 3 different terms. It's going to be the mean of this sigma squared ux plus the mean of the bias squared, and finally we're going to get the mean of our variance. In words, it implies that the risk can always be decomposed into 3 different parts. The first part that we're going to get is usually called the model variance. That's this part that we have over here. It is in fact related to the variance of this ui that we have over here. Well, we should realize that that model variance also has another name. It's usually called the so-called irreducible risk. And the reason behind that is because of the fact that you should realize that in any kind of model, there's always a part that we can actually not explain. And that's also in this model that we have over here, because of the fact that even though it is possible to explain this part over here with respect to what we observe, the xi's, we should also realize that this ui cannot be explained simply because of the fact that, well, we do not observe the ui. So any variation that we have with respect to the yi's that we have over here, well, some part can be explained and another part cannot be explained. And that implies that we can also not, in fact, reduce the risk more than essentially this part and that part that we have over there. So that's the reason why we usually call this irreducible risk. That's the part that we can actually not say reduce with respect to our risk. In that sense, it's not that important actually for for our prediction exercise, because of the fact that it essentially implies that we cannot actually affect it ourselves. But take into account that that implies that, for example, in our particular case, we did of course have a model variance equal to 0.25. In the example that we had so far, we assumed that UI had a normal distribution with a mean equal to 0 and a variance equal to 0.25. And that means of course that, the model variance was equal to 0.25, and that implies that the risk that we have can never be below 0.25. Anybody who is going to claim that he or she has a prediction method that can give us a risk lower than the 0.25 that we have over here is not saying the truth in that sense. And in that sense, it might be interesting to go back to a slide that we had before, actually all the way over here, in fact over here, because of the fact that there we have been estimating at a particular moment in time our risk based on this very large test sample that we had, and then we found out that for k equal to 7, the estimated risk was equal to 0.2813. Well, this is exactly correct because of the fact that we should realize that this is indeed larger than 0.25. And that implies, of course, that somebody might actually say this risk is still quite high because of the fact that it's far from 0, but take into account that it's not that high given the fact that the lowest that we were ever able to get is 0.25, and we're not that far away anymore from 0.25 by using this k equal to 7. Well, then scrolling back to our last slide, this slide that we have over here, we should realize that there are also two other components with respect to our decomposition. That's first of all the bias squared, that is this component that we have over here. We should realize that any kind of model that results, or any kind of estimation technique that results into an unbiased estimator will have that this term that we have over here is exactly equal to 0. And then finally we also have the variance of the estimator, that is this part that we have over here. We should realize that any kind of estimator has of course a positive variance, and the reason behind that is because of the fact that we should realize that estimators are always based on the data, and because of the fact that we assume that the data comes to us in a random way, we're always in some way affected by the randomness of the data, and that implies that we do have a variance. We do have a strictly positive variance. But this of course implies that given the fact that any kind of risk always depends on 3 different positive terms, this term, that term, and that term, and given the fact that we cannot do anything about this irreducible risk, that implies of course that at the moment that we would like to get a good predictor, then what we should do is to try to find that predictor for which the bias is as low as possible, as well as for which the variance is going to be as low as possible. And then we always are going to have our best predictor. However, we should realize that it's not as simple as that. And the reason behind that is because of the fact that you should realize that there is a so-called trade-off between the bias on the one hand and the variance on the other hand. That's to say that models that usually have a very low bias typically seem to have a very high variance. And on the other hand, at the moment that we're going to look at a particular, method that has a very low variance, that method usually has a very high bias. And that is easy to understand by looking, for example, once again at our example of k nearest neighbors. What we should realize is that if k is going to be small, then that particular situation, and for example, if k is 1 or 2, in the most extreme case, of course, k equal to 1, then we should realize that then we have a very low bias. And the reason behind that is because of the fact that then we are very close in terms, all the observations that we're going to have are going to be very, very close, in fact, to the point that we would like to predict. In order to understand that, maybe the best thing to do is to go back all the way over here. In fact, maybe the best thing is to do, in fact, to this picture that we have over here. And we should realize that at the moment that we are going to have that k is going to be small, it implies, of course, that suppose that we, for example, would like to predict this point 1 that we have over here, that, say, the points that we're going to use are going to be quite close to, in fact, the what we would like to predict, in this case, at a value equal to 1. It implies, of course, that the bias is quite small in comparison to a situation in which, of course, we would have used a k much larger, because of the fact that if k would have been much larger, well, then I would have used many points that are actually quite off in terms of where I would like to predict. And most likely, and that's also what we see over here, the function will be quite different. The best prediction function will actually be quite different in points that are further away. But they are, of course, quite the same at the moment that I'm going to be quite close to this point 1 that we have over here. So therefore we should realize at the moment that I keep k quite small, then the bias is going to be small as well. But we should also take into account that the variance can be actually quite large, and the reason behind that is because of the fact that I'm going to base, in fact, my estimator on very few observations. I'm going to take the average over very few observations and actually limit, if k is equal to 1, of only of one particular observation. So that implies that then the variance is going to be extremely high. On the other hand, of course, at the moment that I'm going to have a situation in which k is quite large, for example, k equal to 50, well, then I will use many observations, which means, of course, that the variance is going to be small, but the bias in that particular situation is going to be extremely high. And that implies that what we should do in order to get a best predictor is to find, well, a balance between the two. We should usually, the best predictor is not, say, the predictor that has an extremely low bias or an extremely low variance, but it's usually a predictor that balances, in fact, the bias on the one hand and the variance on the other hand.